All right, so I'm presenting the semi-supervised classification with graph convolutional networks from iClear in 2017. So I guess the point of this paper is really just to get a first order approximations of spectral graph convolutions. And so anyways, here we classify nodes in a graph where the labels are only available for a small subset of nodes, aka semi-supervised learning. And however, one issue with graph Laplacian regularization is that it assumes that connected nodes share the same label, which is a very, very simple and bad smoothing strategy. And you're limiting yourself because you're not truly representing the graph. So as I say, this restricts modeling capacity as edges may contain complex information beyond simple similarity. All right. So, so yeah, label propagation is what they do for smoothing the graph, and I guess there are other ways to get around this, like skipgrams, but they're actually really difficult to optimize. So therefore, the graph convolutional network solution is to encode the graph structure via a neural network with the input and an adjacency matrix, which gets out of the way of regularization, which smooths and loses information. So anyways, this is our loss function for semi-supervised learning. So the L naught over here.
Just a bit slower. We know, but so you have the nodes, which could be events in our case or something else.
Yeah.
And then you need the connections. So you need to build.
Yeah. However, this paper doesn't do it with
okay, but
events.
That is not a trivial thing, right? I mean,
yeah.
They're algorithms, but they are quite computational and costly.
Yeah. No, this paper focuses on like citation networks, like whether or not a paper is a machine learning paper or it's a bioinformatics paper. So I guess on my current train of thought, if you have a node and you have it labeled as a machine learning paper, well, there could be some nodes next to it, some papers next to it that are unlabeled, but they might not be machine learning. But this regularization kind of just makes them all machine learning papers, whether or not that's true. And it forces actually, yeah, the loss here kind of forces it to. So here, J is the neighbor, I is the actual node, and we're trying to minimize, the loss here. But if the loss that we're trying to minimize too is a machine learning paper, when in reality it's a bioinformatics paper, well, we're not going to really represent the graph and do predictions correctly.
Is X the node?
X is the node.
And then A is the
yeah. Mm-hmm. Yeah. Mm-hmm. And yeah, F is the neural network. Yeah.
So there's a generic way of building the graph hierarchical via these cost functions. You're not worrying yet about anything else, but just building the graph.
Yeah.
The graph convolutional network.
Yeah.
And and the standard way to do it is via these two cost functions.
For semi-supervised approaches, yes. Mm-hmm.
So, do you mind letting Himanshu in from the waiting room? Sorry.
So I had a quick question.
Mhm.
F of xi is like the prediction of the neural network for that
Yeah.
node
Mhm.
xi. So what this says is you want the predictions of similar things given by the adjacency.
Yeah,
variance
based
to
off
be
of
similar.
label smoothing,
Yeah,
which
just
is
labels.
bad. Yeah.
Yeah, I mean, but for some regularity, like if two things are very similar, you don't want the predictions to be wildly different, basically.
Okay. Yeah.
Something like that, right? Like if you just had the regularizer, then it would just be labeled smoothing, right? Like
Mhm.
based on the juice. So it kind of makes sense a little bit.
All right. Am I good to go to the next slide?
Yep.
All right. So, anyways, this is what they actually. This is the solution they come up with. First, this is their contribution. So imagine that we have I guess a node A in a graph. Okay, over here. You can see the mouse, right? Okay. Yeah. So yeah, we have a node A in the graph. It has connections to B, C, and D. And B, C, and D are not labeled. So anyways, here what they do, they take the adjacency matrix between the four nodes. You can see only A has connections. And then they, I guess they add the identity self connections to the adjacency matrix. So then here we end up with this, A, B, and C, A, B, C, D. And then each node here has a feature vector. So these feature vectors are given by the data set, the dimensions, like how many features they'll have. So anyways, then we next consider the degree matrix here. So A is with including itself, it's connected to 4. Okay, B is connected to 2, C is connected to 2, and D is connected to 2. And then we want to use that to normalize the adjacency matrix. So then we end up dividing by the degree per node. So in the adjacency matrix for for the connection between A and B, it would be 1 over the square root of their degrees. So in this case, 1 over square root of 8. And then, so that's pretty much this part. And then, so afterwards, they have a projection matrix to go down to take the graph information, okay, how they encode it, and take it down to a reasonable number that they can work with. So anyways, this is the projection matrix. And then here, this is a weight matrix per layer. So anyways, the here, HW is just the projected feature vectors for all nodes in the graph. So anyways, so our end approximation would just, for the graph, the main point of the graph convolutional network is that we have a matrix here with the normalized adjacency values here. And then for rows for A and B together, here's where the multiplication would be taking place. And anyways, yeah, that would be our approximation for graph convolution. So, and I guess I did mention that here we normalize to prevent exploding and vanishing gradients, because when you keep doing multiplication over and over and over, you don't want them to spike a lot. So that was a lot. If anyone wants to ask questions, this is totally fair. But if not, then I will move on. Yeah.
So Yeah, so those are like the skip connections, right? Like
Skip connections?
yeah, those self
Oh, yeah,
Self
self. Yeah,
nothing,
yeah, yeah,
yeah.
yeah, yeah, yeah. Uh-huh.
Yeah.
Yeah, you can view them as
Especially
you can view them as skip connections. All right. So, anyways, so here, so this is pretty much the solution of the paper. This is what. So then here's how we derive it. So given I guess yeah, given a signal x with a filter g of parameterized by theta, here x can just be like I don't know the first part of each like the first entries of each feature in a graph.
So what is this vector graph convolution all about? You explaining it now?
Yeah, so I'm gonna go. So I'm gonna
So-
explain. So how we get from here to here. Mhm. So, anyways, we have we consider convolution here. However, we get these eigenvectors, the matrices of eigenvectors through eigenvalue decomposition, which is very costly. And then also here, multiplication with eigenvectors is an n squared operation. So in a paper from 2011, they spectral convolutions were approximated using Chebyshev polynomials, which are here, right here, and they this has a linear complexity of the magnitude of the edges, which is a lot faster than where we're at right now than this. So here, there's no need for eigen decomposition. And using the Laplacian matrix, which is just the degree matrix minus the adjacency matrix.
I got a little bit lost. So the spectral graph convolution is a specific convolution that you do with graph neural networks?
Well, they consider, yeah, they consider it and they want to basically make this have better performance.
Okay.
Yeah. Mm-hmm.
And when will you apply this spectral graph convolution? What are good examples? Yeah, when does this make sense?
Like in, I guess like nodes in, like for event-based vision or for like
general in a graph.
If I mean, I guess for learning like features among nodes and neighborhoods. Yeah.
So it's the standard technique.
Yeah.
Used in graph convolution.
At the time, at the time, that was the standard.
And when you were at the beginning, so you have some data that isn't living on a regular grid, so you put it on a graph like events. And now you put your events in, and you have a loss function, whatever that is, like segmentation, labeling, flow estimation, that's your L0. And then the standard technique is to regularize this way, what you showed at the beginning.
For semi-supervised. So if you don't have all like labels, yeah.
If you do not have
all
your labels,
yeah.
then you want to fill in. And with the spectral graph convolution, that's the dominant approach.
So it's just making it, I think, more computationally efficient.
Yeah.
Like it's just like the convolution, the way it's defined, like in Fourier domain, it's just multiplication, right? Like convolution, the time. So it's basically, let's say you have a graph, you keep building representations on each other, like layers. Like I think like transformers basically, like you keep improving the vectors with different things because you still end up with n features which are for each of the groups. Like at the end of one convolution thing, you still end up with all.
So instead of like in a convolution shifting the window over to line to learn the kernel, you're doing here something in spectral domain.
Yeah, over the neighborhoods.
So you're borrowing Fourier concepts.
Yeah. And I think eventually you'd probably take the vector and then use a softmax to like or softmax
some sort of activation. Yeah, anyone.
Yeah, any activation function to decide a label for that specific node.
Okay, but this is the way to to learn to apply your convolution.
Yeah.
Okay.
Yeah. Yeah. Thank you for clarifying. Yeah. So, anyways, so we just remember this Chebyshev polynomial, and then we simplify it here. So the authors, they constrain K here. They constrain K to be 1 here for, I guess, overfitting reasons that they explain in the paper. And anyways, they also constrain the parameters here just to reduce the number of parameters to prevent overfitting. However, they still have a exploding and vanishing gradients issue with when their eigenvalues are still between 0 and 2. So they have this renormalization trick that I think they present next. Yeah. So that was the renormalization trick here. This is just the self connections or skip. Yeah, the self connections per node. So basically, yeah, you just add an identity matrix at the end, and then and then also the new complexity is the edges times the number of filters and the, I guess, how many dimensions your feature vector has, which is still better, way better than doing like eigenvalue decomposition and I guess, where was it? Yeah, way better than this. So it's pretty much just a faster way of doing spectral convolutions. So what they do, and then they oh, sorry.
Very quickly, are there any other benefits other than computational complexity of using spectral convolutions?
I mean, the accuracy is maintained. So I mean, later at the end of this paper, they show that you can, I guess, get just as good results. Yeah, this is mainly an efficiency paper. Yeah. So anyways, later, I guess in one of their examples, they use a simple 2-layer model for semi-supervised node classification with cross entropy as their loss function. And I guess, yeah, they use batch gradient descent using the full data set with sparse dense matrix multiplication. So here is just a figure from their, oh, good, it's coming out well, from their paper. So here we have nodes here, and then they get like the same set of weights are used for all nodes. So you see here that not every single node has a label. We only have 2, like literally half of them are labeled. So a single value here, this is just a single scalar value, which represents, I guess, the first feature in a document from a specific node. And then here it goes through hidden layers, and then we get our activations. Some are labeled, some are not. But this is, this basically, I'm just trying to say that this works better than label smoothing or the Laplacian regularization. This was from the supplementary of the paper. So the authors, one way, I guess, in graphs with coloring them, you can test for isometry, which is just like if 2 graphs, you know, have a different structure, can they be changed, but the same labeling, can they be changed to have, I guess, the same structure? So here, it can be viewed as a differentiable generalization of the Weisfeller-Lehmann algorithm, or test, if you want to call it that. So what they do is they assign labels by hashing a multi-set of neighbor labels, and then they perform a weighted sum of the neighbor features followed by activation function. So here, even so here the hashing is actually replaced by the graph convolutional network. And in this, they take an example, an untrained graph convolutional network, and they pass through this graph, and it can here it accurately labels an untrained graph convolutional network. It accurately labels the classes. I forget which data set it is. But yeah, it's just proof that this is more robust. So here are some results. So here we have all these are just like citation, and then here Nell is a knowledge graph. This one's a lot more general. And one thing that's important is that they only use like 20 labels per class for citation networks. So they're like, for example, here, they're only using like 140 examples. So not too much data, and they still get a pretty good representation. Here they do outperform the main competition with Planetoid as another graph method. So here they're just comparing their own, I guess, the evolution of their contributions. So here with k equals 3 and 2, they get 69 on Sightseer. But then after they lower k and do the renormalization trick, they get 70%. It is a very marginal, like very small improvement for all, pretty much for all of them.
For classification tasks.
Yeah. These are all
200 categories. So.
Yeah. So in efficiency here, this is the main result of their contribution. So graph convolutional networks are not easy to implement. The math wasn't, super, maybe not the most fun thing to do. So on the Sightseer data set, their model converges significantly faster than Planetoid. So 7 seconds versus 26 seconds is a like 3 to 4 fold improvement. So this is good because then you could work with more dense graphs in the future if you use this. So finally, they show that they do a t-SNE plot, and with only 5% of the labels, the model learns to, separate the classes correctly. Some limitations. So the main one is that they cannot, because graph convolutional networks are not, I guess, easy to train. Deep models are, they give a lot of difficulty, and they do suffer from over smoothing the features. For the graph structure, so it assumes undirected graphs. Ideally, a directed graph would give you more information. Yes. And then finally, memory usage. So full batch gradient descent scales linearly with dataset size, and mini batching is required. But I guess it's kind of true for everything. So this was, I guess, the main source I used for this presentation. If there are any questions, please let me know before I start the next paper.
Okay.
Are there any questions or no? Oh, okay. All right, good.
Okay.
All right, I'll start the next one. All right, so then the second paper, this is more related to what we all do in this room. Will be a lot less mathy and probably a lot easier to explain. And also, I think like a quarter of this room has already read it. So, anyways, asynchronous event-based graph neural networks by Simon Schaefer, Daniel Gehrig, and Davide Scaramuza, and CVPR 2021. So basically, the problem that this paper considers is, I guess, event-based, images. So we have the traditional dense methods, which are just you take all the events and then you stack them into an image. However, this approach suffers from aliasing, and you lose a lot of information. And then also, if you do this approach, you're not really being sparse. You're processing a lot of empty pixels. So anyways, the authors, they talk about processing events as evolving spatial temporal graphs. Previous works that wanted to do graphs for event-based vision, they would just use static graphs. But the innovation and I guess the contribution here is that it updates activations asynchronously. So when a new event arrives, I should have changed that to they. Yeah, they only recompute the local neighborhood, which saves a lot of computation, whereas previous methods would recompute the whole graph, which is kind of a waste of computation. So, and then also it preserves microsecond resolution. So, I mean, if you're putting an event camera on a drone, I don't think you'd want to wait like 50 milliseconds to process, to wait for the whole batch to come in and then act. But you would want to process it only within the local neighborhood. So anyways, the contributions. So it's straight from their paper, a new paradigm for processing events sparsely and asynchronously as a temporally evolving graph. It has efficient update rules. That's the main contribution, in my opinion. And it can be trained on synchronous event data and tested asynchronously. So the reason they do train on static batches, but the reason they do that is because GPUs are just not made to handle one event by one event, because then that would just take forever to train. But if you put it in a batch, it's a lot easier in a practical manner. And then finally, they apply their method for object recognition and detection while using a lot less flops. So I guess one analogy to really understand the synchronous versus asynchronous, if you have a spreadsheet and then every time you add one number, you force the computer to recalculate every single cell in the entire sheet. But that's safe and easy to implement, but it has a high cost. However, in event-based vision, we do not want to do this. If you add a number in one cell and only another cell depends on this, and then only one cell depends on that, you would only update those 3 cells instead of updating the whole spreadsheet. And both give you the same exact result. So yeah, what they prove at the end of this paper is that graph activations of a whole static batch are the same as the graph activations if you go event by event. So this is their whole pipeline, straight from their paper. You have here the sparse point cloud, all right? Then they do some subsampling. They subsample by a factor of 10. This is to prevent overfitting. Then they construct the graph, and then they pass it through a graph neural network, what that they make some tweaks to, and then you have object recognition. So for graph construction, so here we have a graph which is vertices and edges. They're dealing with directed edges. So they subsample by a factor of 10, yes, as I said on the slide before. And then what they do, they scale time to match the spatial dimensions, because in the loss function, if like the event camera is like in microseconds. So I guess, microseconds are huge. And if you didn't scale down the time, then you would have, I guess, the time portion dominating the loss and the propagation. And then finally, they create an edge. Yeah.
Yeah, I didn't understand the temporal normalization.
Yeah.
And also like how do they make this into a directed graph?
They didn't say much about how.
How?
Yeah,
So
but I mean, it's
temporal?
time. Yeah.
So just temporally it's
Yeah.
directed.
Temporally, it's directed. Whereas in the previous paper, we were just dealing with like papers.
You still have to choose something in the X, Y. Right. I mean, you have to make just probably a definition, just go from the left top corner.
Yeah.
Yeah.
I thought every time step was like one instance of the graph and how the graph is evolving, or you take that entire point cloud as a graph and the directions are like.
So you take it one by one. But and I would say both statements are true, that you take it one by one, and then those one by ones make the graph.
So the graph is this entire 3D thing.
Yes.
2D image.
Yeah.
And
so
that is one.
Yeah. It's basically it is kind of, you can think of it as like a bunch of 2D. It's like a video, like a bunch of frames stacked, but it's a very like asynchronous video and like very fast video.
So you don't have to wait for all of them to stack up. Like every frame you want to
No.
something.
Yeah. Every frame. Yeah. Or time step.
And the time normally, I didn't understand the temporal normalization.
They normalize the time because then later if you take they do representations based on time. However, like if you have like a time that's like 5 million microseconds, however, and you only have like a difference in pixels of like 5, well, then the time is kind of dominating the loss. No matter what, you're going to have a terrible loss.
So I believe they learned this from my paper. So
okay. We got the celebrity in the room. Yeah.
First one actually to use convolution on events.
Yes. So basically, temporal normalization is you have an X, Y, and 2 milliseconds, right? And if you don't normalize anything, it will be a thin slice of events, like an image. Because 10 milliseconds is really thin. X is like 480. 640, 480, and 10 milliseconds is really thin. It basically expand the time to make it also fall in the ballpark of 500 of pixel wide. So if you visualize the events, it will be like a square-ish, not like a pancake thin slice. And the key reason is the next on the right. So they also use a radial search, so the KNN, to search for where's the neighbors. So if you want to neighbor search 10 years neighbors, you need to maintain that, okay, in a space of a ball in a radius, you want X, Y, Z to be roughly the same density. So basically just multiply time to make it.
But you basically bin your time dimension in a number of bins that's equivalent to the X, Y dimension.
Not bin, it's like multiply the time dimension so that the numerical value has the same range of the X.
Okay.
Like this, the beta, like, yeah. Like,
yes,
yeah.
Exactly.
Yeah.
Just multiply by.
I also
we have a
I was wondering, do they mean center the event cloud every time for each frame?
I don't think they said that in the paper.
Okay.
Yeah.
Because the graph would change every time, right? Yeah, if the time keeps changing.
Wait, I didn't hear the last part.
Like, so the graph is based on the XYT, like event locations, like the 3D location and the connections between them, right?
Yeah.
So if you don't mean center them, you will have to basically create a new graph every time.
Okay.
Is that,
Means,
does it make sense or not?
yeah,
Can
time,
you turn up the volume?
Okay. Yeah.
yeah, so the time is normalized by subtract by the first event time in that slice. So in every slice, time starts from 0 to after scaling, maybe 4,500 if you're on 645 for yeah.
Also, something continuous parts also just
when you are training it, you use a slice, right? And you don't want the time to be like 1 second in this slice and start with 600 seconds in another slice. You normalize it by that.
Mm-hmm.
Okay.
Yeah, so I also had some similar questions. So this time scaling, is it the same as adjusting the time resolution? Like, does this process like each microsecond or each 100 microsecond?
Yeah, that's a good question. It's not changing the resolution per se. It's just expanding the numerical value of time, just multiply all the time by a fixed factor. And then the main goal is to get the time range to the same range.
So you said like it's sliced, the data is sliced into time periods, right? It's sliced.
Yes, yes.
So what's the time resolution of these slices?
You can determine that.
Yeah, they didn't say it in the paper, but that depends on task by task. Here they're not testing on, I mean, they're not training on anything crazy fast. So I imagine like they could probably get away with like 0.5 milliseconds. And
so what happens if some events with like finer time resolution happen in this time period? Does it buffer these, keep it, and then with like
Wait,
what happens if some fine resolution events are received from the sensor? Is it buffered and then processed with lower time resolution?
sorry, you're gonna have to repeat that. You said what happens
If the sensor generates like microsecond resolution events,
yeah, yeah,
and the processor wants to slice like with millisecond resolution,
okay.
how would the events that happen in between, how would they be handled?
Well, so in this paper, they do downsample by a factor of 10, but they also do synchronous training. So they would, I mean, the time would be scaled down too. But they're if what you're trying to ask is if they're dropping events after they do subsampling, they don't drop any more events.
Mm-hmm. Okay. So basically, this time scaling is like adjusting the time resolution, basically, right? It's about sampling and adjusting the time resulation, the intervals where.
I think it's just adjusting the numbers to make them equivalent in the deep learning.
It's a multiplier clock.
Yeah.
Oh, but usually when they use graphs, they downsample, so they don't take every event as a node.
Yeah.
Okay.
But like
Thank you.
N's or so here in this
Yeah.
class.
Yeah. So, yeah. Thank you. Yeah. So it just depends on what you set beta to here, really. The authors didn't say in the paper though what they set beta to, and I didn't look at their code.
Their code, they're hard coding the conversion.
Like, in their code they hard code it.
Yeah.
Oh wow. Oh.
Like main error and times some constant and add something.
Okay. Yeah. So that's.
What are they hard coding? Can you say?
The normalization of T.
The normalization of T. Okay.
It might be like 0.001.
Oh, okay. Okay.
Like thousands, right? If you want to get into the same size of the sensor.
Oh, I guess it depends.
Oh, yeah.
All right. So anyways, here is the asynchronous update rule. So instead of recomputing the entire graph for every new event, GCNN exploits locality through recursion. So here you have a new event here, I prime. All right. And then here it only affects the immediate neighbors. Okay. So in the first labor, the one hop subgraph, that just means like you hop over 1 degree, and that's the subgraph here. So that only that would update. And so yeah, and that goes on and on. And then finally, the activation is, it depends only on the subgraph, not the total graph size. That's the main contribution. So yeah, so here, this psi and this gamma, these are just MLPs that do this job. And here's the new node. Here is a neighbor. So here, this is a J in the neighborhood of I, and then this is the edge between them. And then finally, this MLP just waits. I guess it takes the internal state and the external activations, and then waits. I guess this decides the class for all neighbors. So.
This is during inference only.
Yeah, only during inference. Yeah. Training is done normally. So anyways, yeah, function C where psi computes the messages based on the pairs of neighbors, and the messages depend on the node features at those nodes and edges and how the nodes and the neighborhood are spatially arranged. And the messages are aggregated via summation, and then you get a new value after passing it the activations and the initial node through an MLP. So I guess here's a fun way of thinking about it. So if you have like a social network of voters in an election, and if you're trying to decide your political stance, suppose you're undecided, you're 0.5. Okay, one of your neighbors is very right, give him 1.0, and then the other one is very left. And then your edge is the, yeah, I guess the relationship between, yeah.
No, not friend.
Yeah, actually, I'm gonna get to that at the end because because some papers actually build up on that. So here, the size, the computing the messages here. So don't copy your neighbors, but instead interpret them based on who they are and where they stand relative to you. So basically, in a normal graph neural network, if like, I don't know, node J says I voted for A, then only that message is their value. But this paper has an interesting way of, I guess, understanding their value. It actually uses more of their geometry through a spline convolutional neural network. So it pays attention to their spatial arrangement. So here, the edge isn't a line, but rather a vector describing the geometry. So suppose like neighbor J is 4 pixels up and 35 microseconds beforehand. And then the network, the spline convolutional network, C or psi, says that if the neighbor is to my left, then treat their opinion differently than if they are to my right. So you might trust advice from a close neighbor than, compared to one you don't talk to as often. So anyways, after summation, you get their total message. And then the update, the other MLP is given your own previous opinion and everyone else's opinion. Then you make your own opinion. So that was a nice little analogy. One thing they don't take into account is whether or not you actually like if you like your neighbors and you like their beliefs or not, and you agree with them. But future papers, I guess, take that into account. So, anyways, here's the network architecture. This is pretty simple. Just, a bunch of graph convolution blocks. And actually, this is pretty simple. Oh, one thing. This is pretty simple, similar to the math that I presented in the first paper. So, so this would be like this comes from the adjacency and the degree matrices. And then this would come from the projection and activation matrices from the previous paper. So anyways, so this is their architecture, pretty simple. Yes, they use spline convolutions, which lets the network learn from the relative positions, the spatial arrangement of nodes, graph neural networks don't do this. They also do voxel grid pooling. So they employ a grid-based pooling strategy. And features are aggregated via max operation. And this step is also updated asynchronously. So I guess, here are the training details. They're hyperparameters. They do it. Quadros are not very strong. So but also they're just doing classification. But even for object detection, it shows that their method doesn't require a lot of compute and that their recursiveness comes to their benefit. Finally, all right, so here's the data set and cars. So here, at least this is the amount of flops they use. They use 200 times less than the next best graph-based method. So really, like the computationally, this is a big contribution.
It's what they do a detection of cars.
It does both. Well, it does both, but I think this one's just for classification. Just recognize them. But I mean, all these data sets, they have object, like bounding box too. So, and then for object detection, on the Gen 1 automotive data set. So it has higher accuracy, outperforming the state of the art asynchronous method by 3.4%, mean average precision, and then while having a lower latency. So it 129 milliseconds compared to 1,000 plus milliseconds. So that's huge.
129 milliseconds.
Mm-hmm. And then
inference.
Yeah. On 25,000 events.
5,000 events.
Yeah.
Okay, which is the tenth of a second.
Yeah.
So it's real time.
Yeah. Yeah.
Object detection, and they put this input an event slice for that time.
Yeah.
And they subsample the events by 1,000. By
a factor of 10.
By
Yeah.
a factor of 10.
Mm-hmm.
And then the slice keeps going, or then they take the next slice.
Well, then the next event comes in. For inference, they're not using slices, but I mean, I guess they
so
take.
It's a continuous update.
Yeah, it's a continuous update. Yeah. Mm-hmm.
I think they maintain a graph of constant number of event, and as new event comes in, old event will.
They slow down.
Okay, so then they slide the window.
Yeah.
Oh, okay. Okay.
But they also need to build the graph, so that's built asynchronously on the run.
Yeah.
They're just using the first few 1,000 of units of events to build the initial graph and update it afterwards.
And that's so fast. So this is basically real time.
Well, the
data
set is small.
Yeah.
The data set is super small. I mean, what do you mean in size? The images are so small.
They run inference on 25,000 events, which is
actually that's
not
small. Like from my own work, I would say 25,000.
Okay, for you it's fast. Okay.
Yeah, that's
25,000 events on
like I could get, yeah, that's actually really not a lot. Yeah. So maybe not as real time as we think, but no, it's still very, it's still way better than everything previous to it at the time. I mean, this is back in 2017, and it's also done on a Quadro, so which aren't the fastest GPUs.
No, but you ran it recently to show on the, okay, yes, gesture, that's very small, yeah.
And what A6000s?
At the time, almost all the time is spent in updating the graph, because you need to figure out like which of the event are the current one and which are the oldest one.
So building the graph
Inference is
challenging.
Yeah. All right. So anyways, key takeaways, this is fast, and but you still get good results. So anyways, that was the presentation. If you have any questions, please feel free to ask. And if, So yeah.
Thank you for the presentation. It was really interesting. I especially like the second paper. It seems promising, especially for implementing AI tasks on the chip. So all these methods that reduce the complexity give us hope that there's a chance for them to be implemented on the hardware. So from a circuit side, it's interesting. Yeah.
Thank you. Yeah, I also preferred that one too. So yeah.
The update, it still seems that graphs are built with certain data structures, right? KD3 something.
Yeah.
If you apply it directly to the events, there are limitations probably for the energy.
Yeah, I mean, also, that depends on how much faith you have in point clouds. So yeah, I mean, yeah, for me,
yeah, right.
Depends on your application and on your task.
Create
Yeah.
some intermediate representation that already groups the events that we're trying to do with the vector, or maybe there's something else that can be learned that's better. I think that's the way to go.
Yeah, rather than having every
event as a node or even downsample. I mean, our own Howard was the first one running graph convolutional networks, and then the goal was we wanted to demonstrate that we can do long sequences, right? We will process the second half of second, in order to get challenging segmentations.
Yes.
But that probably was a major effort.
Is there?
So we didn't do it asynchronously, but we
yeah.
I think we're good. Yeah. All right.
questions? Some more?
Thank you.
Thank you.
All right. Thank you. Yeah.